Good morning, everyone. Welcome to this webinar. It's the 38th ETP4HPC webinar, and I'm Pascal. I'm ETP4HPC's communication manager, and my colleague Gabriela is also here to help run the webinar, and especially the questions. Her help is precious when we get to the questions. So for those of you who are not familiar with ETP4HPC, I know there are not many of us in that case, but still, we are a non-profit association that promotes European research and innovation in HPC and neighboring areas. And we are a private member of the EuroHPC JU. So before we get into today's topic, I have a couple of practical information for you. This webinar is recorded. You will receive the link to the recording tomorrow. This webinar is in listen-only mode, but you will be able to ask questions. There is a question tool that you can use to ask questions. You can submit your question at any time, but we will take questions at the end of the webinar. Otherwise, it's really too complicated for speakers. Also, you can download handouts from this webinar. There is a handout section where you will find the slides, the 3 presentations for today, so you can download them right away. And yeah, that's it. So yeah, today we welcome participants from Castel 2 and EuroCC in our webinar. So hello guys. And now to the speakers. So we have a lot of speakers today. I'm happy to welcome Craig Prunty from Cyprel, Utz Overhouse from HPE, Xavier Teruel from BSc, and Manolis Maratsakis from Forth. So I will share the agenda so you can see who handles what. So before we delve into OpenCUBE and RISER, which are the 2 main topics today, we'll have a short presentation by Craig Prunty about RIA-1 and SEN, which is very relevant to both projects. So it makes sense to start with that. And then we will address OpenCUBE and RISER, and we'll have your questions at the end. So, time for our speakers. Hello, Craig. I will promote you to presenter so you can share your slides.
Perfect. Okay, can you see this okay?
Yeah, Cyper in a nutshell. That's
Okay,
what I
so
can
just
see.
perfect. So just a few slides to explain Cypro,
5 minutes.
the RIA-1 platform and the RIA-1 processor and the SEN platform, which is our server that we're using for the RIA-1 processor as evaluation and internal in-house evaluation and custom evaluation. So if you're not familiar with Cypro, we're a European company developing, born out of the European Processor Initiative, developing CPUs for server. And as the #1 server application or the #1 server vertical is high performance computing with our RIA-1 processor. We're about 200 employees. We're headquartered just outside of Paris, France. And our seed funding came from the EuroHPC JU through the European Processor Initiative. So as part of that, we have 28 partners in the EPI that create a kind of an ecosystem for our RIA-1 processor and beyond. And then we're in a number of different projects, 2 of which are OpenCUBE and RISER. And in these, our participation is really around the hardware piece and porting software to the European processor RIA. Our processor is based on ARM. You can see here a kind of a quick overview of the RIA-1 processor. It's a monolithic chip with 4 HBM stacks in package. So it combines both HBM and DDR5 with the ARM Neoverse V1 core. So you can see a blow up here, some of the different elements we have, the PCI Express Gen 5, DDR, HBM in package along with the cores in the center. So the SEN server, we're not a server company. If you saw on page 1, we're partnering with a number of OEMs and ODMs. Utsuve from HPE is one of the partners we've announced with. But we do develop servers, and this is for a number of reasons. So it's a reference design for our customers who do build servers. Internally, it's an evaluation board so that we can test our silicon. And then it's used for software porting, our verification and characterization, and then demos with customers. So that's the idea behind this platform. It's not something that we make many of, but the goal is to make it as flexible as possible and to be used in things like this program where you might do software porting and evaluation of performance both. So if we look at the way the CEN is configured, it's a flexible platform. Everything is on PCIe riser cards. So there's the board itself that holds the processor. It's a single processor to a motherboard. Internally, then there's slots for accelerators, for NIC cards, 2 NIC cards on the back, and then also some SATA. There's basically a SATA block that can hold 2 SATA ports, or has 2 SATA ports, so you can have disks in chassis as well. And then a power board and COM board just for general IOs. So if I break this out in terms of the IOs themselves, you can see here listed the EVB, which is our motherboard, power board rear IO, the 2 NICs up on top, the SATAs, etc. And the way that these are all interconnected to make them flexible is over PCIe cables. So all of these elements are on PCIe risers, and that allows you to configure a single NIC, dual NIC. And in terms of the configurations, then it's even more flexible because you can have CPU with up to 2 accelerators on PCIe cards. Typically, people would use GPUs for HPC applications, but they could be any kind of accelerator. And this is a platform then that we can use for software porting and performance testing of our RIA processor and our RIA processor with GPUs. Or we could have a dual CPU configuration, which is used quite often in HPC as well. Again, if I look back here, you can see the PCIe cabling configured for a dual CPU. But the different configurations you might use for different kinds of applications. For CPU, there's a lot of defense applications interested in this. Could be AI inference. We see quite a bit of interest for weather forecast with the HBM and the DDR both. So there's a number of different applications. With GPUs, of course, there's more and more porting that is being done in a lot of different workloads to run on GPUs plus CPU and looking at how to optimize that. So that's the idea behind the CEN platform, and that's being used in these 2 projects, which is why we wanted to introduce this separately first. With that, I'll pass back to Pascal, and I think Utz beyond that for OpenCUBE.
Thank you. Thank you, Craig. So, Utz, I will make you presenter. So now we are going to talk about OpenCUBE.
All right, that worked flawlessly. Thank you, ETP team, and thank you, 30 people in the audience. That's great. I'm going to talk about the OpenCUBE project, and in particular the system architecture update. If you've heard about it before, this is the current state, more or less. Maybe we're 2 months further than what I show you because we're working on stuff, of course, that can't be shown yet, but this is an Horizon Europe funded project that comprises ECMWF, KTH, HPE, Semidynamics, Cyperl, and TU Munich as partners. So small in terms of partners, big in terms of ambition, because we want to build a blueprint for an open source cloud-based system on EPI substrate. For those who like this kind of picture, I've drawn a diagram of what we have currently in the lab. We have an external access with a fabric manager node. Then we have 2 infrastructure servers because we need to bootstrap somehow. Those are x86 boxes of no particular interest, maybe. Then we have Ultra-Ethernet. Well, you might say there is no Ultra-Ethernet except for one implementation from HPE, which is the one we chose for getting started, the Slingshot switches. It's one switch in this testbed, a management switch for regular Ethernet, and a front-end switch just to separate the two, to have a back entry into all the system parts should things fail, because we're in experimental mode, right? This is a testbed where we work on drivers. Some nodes will lose connectivity on one of their NICs easily if someone makes an error. Then we have some stock HPE style hardware, just because we could get that cheaply, to have some storage in these DL servers. and we have 4 ARM Ampere Ultra nodes as a precursor for proper high-performance ARM nodes, like the Rhea chip that you saw, which unfortunately is still not in the boxes that you just saw from Craig. And that's why we had to start somewhere. The project is running for 2 years at this point, and those RL300 Ampere Ultra were easily available as a stand-in. On the Slingshot switch, we have enough ports, and in the boxes we have enough space to add the real Rhea nodes. 12 is the target. We have a smart PDU, which you cannot see here. And on each of the RL nodes, we have an FPGA running the Semidynamics EPEC2 bit stream as it is being developed. And just to prove that, I have this small picture on the right for those who want to see a CPU info. So this is a bit stream running RISC-V 64-bit vector-enabled Avispado, so the current upcoming Semidynamics core. There's a pic. Oops, that was too fast. A picture just to prove this is actual hardware discussions and not just wish list thinking. But of course, you can't see anything in these pictures other than that they exist and the lights are turned on. The software is, I think, not unexpected, maybe for each of you, or maybe each of you have some particular interest and will find it here. So on the HPC side, we go libcxi. That's the Slingshot support layer, or could be lib Ultra-Ethernet once that exists, libfabric, which is standard, mpitch on top of that, and OpenMPI, as well as GCC LLVM. That's all easy, more or less. Then we do Podman for containers, and we started with K3s as a minimal Kubernetes installation, going to K8s because that's the more common one as the testbed grows and all the components can properly be handled in Kubernetes. We take a container first approach, so everything is in a container with a container SSH entry point. So that's basically an SSH that when you log in, a container is started for you for your user environment, which is unusual maybe, or maybe exactly what you want. You have your environment in a container. If you want to log into a differently configured session, you choose a different container to log into, and your environment is as the container defines. So no modules needed, no risk of someone ruining your environment because there's a global system update. However, the risk of your container being completely out of date, that's an alternative concern to have as a data center operator. But it's the path forward for these very container-oriented workflows in AI. Management stack, Ansible, of course, because we want infrastructure as code. For IDM, identity management, we use CanIDM, which is a very convenient, small, lightweight, but powerful identity management setup. We'll work with OpenCharmy. That's the open source system management system that is forked from the original Cray system management tools for the Shasta architecture, if you've heard about that, which is in use on Lumi, for example. So this is open. It's community work. It's simplified, but feature extended. And we've already booted the SciPerl boxes that you saw, minus the CPU, with that to see that they can actually be controlled on the OpenCharmy level. We started with OpenSUSE as a operating system, and we'll move to Talos, which is a minimized Kubernetes-ready Linux distribution, which is so minimal that you don't even have a libc or systemd or whatever you expect. Minimal attack surface, very secure, very lightweight. However, quite a bit of work to get that to work with all the hardware components. There's no dynamic loading. It's a bit like a unikernel on steroids, if you know what I mean. Storage, for the moment, is the standard part you would expect, a high-performance distributed system on Lustre. Also Ceph, because Kubernetes likes object stores. We use NVMEs with namespace separation for that. That's maybe not unexpected. And there's also monitoring, because we're still working on a full solution. But in the interest of time, I can't go into that today. It's also work in progress, because there's nice options on the market that we're still considering. So testbed will be expanded. I already said that. We'll get more FPGAs as we get more nodes. we're expecting the 12 REA CPUs as soon as available, and we have more room for storage. We hope to have the full system available in 26. Why can't I progress? Okay, so now on the software side, there are some interesting aspects. I mean, if you believe everything I said can be done out of the box, and I'm sorry for this jumping, I didn't click anything, that's not really the case. Kubernetes is not very good at mixing resources. There's resource labels, but our resources are rather different, right? We have RISC nodes, we have ARM nodes, we have x86 nodes, we have, you'll see in the middle, fabric attached memory in the form of OpenFAM, an API for a PGAS, so global address space-like disaggregated memory access method. Can also address storage, but typically is used with RAM backing or Optane when that was still available. And Kubernetes is not very good at mixing these resources in one setup. And Kubernetes on RISC-V was something that also didn't exist when we started the project. We're using the work of Forth, and maybe the RISER talk will talk about that. Otherwise, you can ask the RISER team how they ported that. So that works well on these cards that we have. OpenFAM is a first-class citizen. So in this system design, you can ask for memory distributed to be made available for data access, read or write, to your allocation, to your job, in a portable fashion. And we'll come to where we use that already on a later slide. I just want to finish on the EPEC2 integration here. So the coprocessor for now is running a bit stream on FPGA, so it's not awfully fast, but it's awfully realistic because it's the real bit stream that will be taped out eventually. However, the host-to-device interface is slightly different from what a real chip would have. There's no native PCI device. I saw Ken in this audience from Xilinx, now AMD. So we had a bit of work to communicate to this bit stream through the XDMA interface that exists for Xilinx FPGAs. But at the moment, we're using these EPEC2 bit streams as a proxy for this CPU coming, which allows us, which we do by running Kubernetes workers on them, and also as accelerators, where we did ONNX offload and we are working on OpenMP offloading. So that's the software side. And I don't know, this is not progressing. Oh yeah, so it's progressing very fast. We also have a application view and picked a few representative use cases from different usage patterns. One is drug discovery, which is a Autodoc workflow in an Airflow-based, very cloudy approach to using resources like this testbed. So ligand screening, many ligands, AI model, looking at that, nicely scalable with Kubernetes. That's one of our use cases. The second one is in between, HPC-like. The IFS dwarfs of ECMWF have been looked at. Two of them have been ported to RISC-V, which is, I think, great news because everybody's complaining about the RISC-V ecosystem being the hurdle compared to ARM for adoption of RISC-V. And these two dwarfs already run. And then there's a second aspect, which is the data wrangling, as Thiago Quintino from ECMWF always calls it. If you've ever seen large dimensional field data, like in numerical weather prediction, that gets produced and then looked at in a very particular way, the subsetting is an expensive operation. And this is this data cube extraction of, say, a flight path of an airplane and all the boundary cells of where that airplane is going through the North Atlantic airspace has both the spatial and the time dimension through your forecast. And getting just the boxes you need from your grid is an interesting question. And that is being worked on by having the field database of ECMWF on OpenFAM. Much nicer medium than Lustre to go through data. The third use case is a containerized OpenMP MPI application, so proper HPC if you want, for plasma simulation inside Apache Airflow again to understand what the results mean and how to analyze them and track the work. So we're covering the cloud to HPC workspace. And just to show you the kind of space weather use case, this is an actual simulation of data run on this testbed. I mean, I could argue that is the case even if it was not, but believe me, trust me, this has been done. And if it's breaking up for you, that's because of GoTo not really streaming videos nicely. But that's what we can do. So we can look at the conditions of a magnetic field under different influences like sun bursts, and get actual data and do the ML post-processing in Airflow for that. So IPIC3D nicely works on ARM, and that's one of the messages. We also did inference, and for the inference we ran with ONNX on the RISC-V accelerators. Now you could say they're slow downers in this case because they run at whatever 75 megahertz, but the concept holds. If you have proper accelerators, we expect a really nice 60 inference per second or so rate, which is a good one for first chip. So that's normal AI fare these days, but we do it on rather experimental hardware. The drug discovery one, similar stuff you would be expecting on any cloud these days, but we're ready to run it on RHEA once that is taped out. The IFS dwarfs are important because they're the core of the IFS system turned into small, not kernels, but kernels with a driver around it to run them independently and understand whether, for example, for an FFT, you have to use these processor instructions, and for matrix multiplication, your caching on this processor allows you to choose tiles of a certain size, and all of these usual HPC experiments that we do. The ones considered here are microphysics for clouds and spectral transforms. They've been ported. There's still work to be done, of course. And of course, there's another level of work when RHEA comes out with actual slightly different processor properties, but the ARM work is done and the RISC-V work is done. For me, very interesting, for some of you who know that I'm also involved in the Destination Earth project on the data layer of moving data from multiple simulations into the analysis steps. This is an interesting concept, different from what we're doing in Destination Earth. ECMWF always saves their data in the field database, and that's a metadata-rich, domain-specific database holding all the forecasts of the last 50 years. So despite resolutions having increased and model changes having happened in the meantime, it's a consistent schema that allows you to query ancient data and data from today's forecast in the same way. But the backend, of course, changes with every generation of hardware. And so it's a good way to test new storage interfaces. The FDB on a proper new substrate like OpenFAM is a very interesting experiment. It's not very durable because OpenFAM goes away when your node goes away. It's not a disk in there, it's DRAM for us, but the performance is very different. Why is that of interest? It's of interest because memory is much easier to write and read from and write to at the same time than disks are, for example, right? And traditionally you write from the simulation, not in checkpointing form, but in every iteration you write to disk just to read it again from all the post-processing steps, like statistics or averages, or nowadays AI inference on certain subregions. And they all compete to read from the disks that you're just currently streaming right to, which is not good. When you do FDB, it ends up being a page-level discussion in DRAM, which is much nicer than rotating magnetic disks. Or even NVMe, which has much larger access block size. Right, and that's the last slide I have here. I'm super quick today, but that leaves more time for questions. OpenFAM is open, right? Like the name says. If you're interested, it runs natively on verbs in InfiniBand or normal Ethernet at lower performance, even TCP if you want. And of course on Slingshot very nicely by natively using libfabric. It has atomics. You could implement your favorite OpenSHMEM on top of it. very low level, but can also just be a storage backend. And that's where I'm closing here. The last slide on distribution. Look at our website for events. And if you don't have questions now, but have them later, reach out to Ivy Peng at KTH, who's our project coordinator, or me, who's doing the technical coordination. Come to our ISC booth at Cypher, whatever you want.
Thank you, Utz. We'll take questions at the end, as I said. So now I will hand over to Xavier to talk about Riser. So Xavier normally should have received a prompt.
Yes, I have it. So let me start presenting and let me switch the.
Oh,
Okay.
we see you. Yeah, that's it.
Okay.
That's fine.
Then, thank you, Pascal.
Thank you.
Thank you, ETP. Thank you, the attendees, for allowing me to present that work. So, Xavier Teruel from BSc, from Barcelona Supercomputing Center. So today I will be presenting the acceleration as a service as seen by the RISER project. So this is a specific use case that we have in the RISER project. So let me start with a brief introduction of the project itself. So in the slide we have the different partners on that project. So starting from the bottom layers in the platform ecosystem. So we have Semidynamics and Cypil. They are providing the processors that we are going to exploit in the project. Then in an upper level, we have Xtool and XSPs. They will be dressing the processors in order to build them in a board and allowing the platforms to be built. Then we have BSC and Forth. We are participating at different levels in the software ecosystem. So since firmware to the use cases. And then finally, we have Cloud Sigma, which is the European cloud provider in the consortium. Okay, so if I will need to describe Riser in a nutshell, it will be something like this. So this is what I call the backbone of the project. So in the top, we have the incomes, the processors, the architectures that we wanted to exploit within the project. So they are coming from the EPI project and the EU pilot projects, respectively. And then at the initial state in that workflow, what we have is the dressing on the PCB. So we wanted to create two different platforms. Just to name them, we wanted to create the microserver platform, which is a self-hosted architecture, a self-hosted platform put in Linux and acting like a plain data center or cluster. And then we have the accelerator platform. The accelerator platform is like a device attached via the PCI Express to a host that will allow to speed up certain parts of the code. Okay, these two platforms, the microserver and the accelerator. So in that presentation, I will focus more on the accelerator platform. Okay. Once we have built these platforms, we need to still work on the firmware and the system software. So we'll need to develop certain services and drivers in the operating system in order to exploit the different capabilities of the system. And once we are advancing into upper levels in the software stack, we'll find software components in the tool chains, like the network object store component that we are based on a Mint.io. And then we also have the containerization support, which in your case is also based on Podman. And on top of that, we are using an orchestrator, which is Kubernetes or Kubernetes-like. Actually, we are using as OpenCUBE the K3s implementation, right? In addition to that, we will need also to have support from the compiler side because we wanted to compile the different use cases and leveraging the OpenMP capabilities. So in that case, we are using LLVM, and actually we will one of the goals of the project is to extend LLVM in order to support the new proposal that it's part of the use case. Okay, here in the bottom of the slide, you have interesting information about the project. And let me move to the next slide. In that slide, what I wanted to show, or the takeaway message from that slide, is the investment, the effort of investment that Europe is doing in terms of the different technologies in order to have this technology independence, based on ARM, based on RISC-V. So in that slide, I would like to highlight the EPI project that was one of the starting projects facing two different architectures, ARM and leveraging the RIA processor that was presented before as well. And then with semi-dynamics, we are exploiting also the RISC-V accelerator. And also we have the U-Pilot. U-Pilot is developing the Beck processor that is part also of the incomes of the RISER project, right? So in that slide, we have also other projects in which BSC is participating. Maybe I can highlight the MIP project, which is creating an experimental platform for RISC-V devices. Now we are working in the VZL project, the Barcelona Zetascale laboratory, which is also leveraging the RISC-V architecture. So plenty of money devoted to that. Okay, then moving on, let me present the motivation for the project, but also for the use case I'm going to present. So in the top of the slide, I have some kind of axioms, some mathematical axioms. So these are realities. So observations that we can do from the real world is that there is an increased number of devices on the data centers, on the HPC clusters. So this is something that we need to exploit, that we need to leverage somehow. And then, in the other hand, we also have a high demand on the cloud services. So this is something also that we need to be aware. And these are the two components that we are trying to mix on the RISER project. Okay, in the bottom side of the slide, we have the approach for the use case I'm going to present. We are going to use RISC-V as the accelerator, and specifically, we will like to exploit that as a PCI device attached to a host and enabling the multi-threading capability of the systems developed by semi-dynamics, but also the vectorization support that it includes in the architecture. In the other hand, I wanted to highlight OpenMP. OpenMP is a well-established parallel programming model. It has been in the industry for many years, and this is the component that we have decided to use in order to offload work from the host to the device. Okay, I will try to expand a bit more about OpenMP, why we are using OpenMP in the project. So, as I said before, this is an open standard. It was established in the HPC community for many years, more than 20 years right now. It is portable. It's not tied to any specific architecture like the GPU devices vendors, or so you can create a program and compile that program, and you can use it and leverage it in different architectures, right? It is flexible, and it means that it is not only intended for exploiting the device capabilities, but we can exploit different levels of parallelism, starting in the host. In the host, we can still use the work sharing. We can still use the task parallelism that is inherent to the host side. But also, in addition to that, we can also target, we can also offload certain portion of the code to the device. And this is what one of the main features that we wanted to leverage from OpenMP. And finally, it's manageable, and it means that we can adapt the execution of the program to the underlying resources. So if we can program an application, we can compile it, and at the runtime, we can decide the number of CPUs that we are going to use. We can decide the number of devices, so we can shrink and span the in terms of resources, the resources that we are using for that specific execution. Okay. These are the goods, but there is one bad thing, right? So currently, OpenMP is not supporting or automatically exploiting the multi-devices approach. Okay, we cannot automatically divide a loop, for instance, among multiple devices. Okay, for instance, here in the top side, I'm presenting the current support in terms of devices. Whenever we are offloading a portion of the program, we need to decide which device we are using. We are providing a single device identifier. So what we wanted to do in that use case is to extend the OpenMP functionality to add an extra level of parallelism, which is based on the spread construct, and then allowing that construct to use a set of devices instead of a single device. Okay. This proposal is based on three main components. So in the middle, we have the OpenMP specification. So what we wanted to do is to propose a new extension, defining new terms, expressing new syntax, defining new semantics, so and writing them into the OpenMP specification, right? And that will become a kind of contract in between the two sides that we have in that slide, right? So in the left side, we have the software stack implementation, and it involves two main components. First, the compiler, LLVM implementation. So we need to add new compiler transformations. We need to create code for that new construct that we are proposing to the standard, but also it requires as well from some runtime support. So we need to handle what is the occupation of the different devices in order to improve the scheduler behavior, for instance, right? So the compiler implementation at two different levels, compile time and runtime. And in addition to that, we need also some system support, system software support in terms of drivers. So we need to have a mechanism that allows to communicate the host with the device in order to offload data from the host to device, device to host, and also to offload part of the code to the device as well. Okay, so this is managed by this driver that is communicating the host side with the device side. And in the right-hand side, we have the use case. So we are developing a set of acceleration use cases, programs that have part of the code that will be offloaded to the device. We'll pay more attention to that in the upcoming slides, right? Just as a matter of example, let me show what is the current support that has OpenMP versus the desired support that we would like to have in OpenMP. Okay, in the left-hand side, what we have is the current support. So if we need to deal with multiple devices in OpenMP, right now we need to manually distribute the work among the different devices. And this is what we are doing here. In that example, what we are doing is opening a parallel region with as many threads as number of devices. So we are creating one thread per device. We are getting this thread identifier that will become the device identifier, that is in TID. And then with that TID, with this thread identifier, what we are doing is manually computing the boundaries of the loop iteration space that will correspond to that chunk. Okay, so we are using thread ID in order to compute the lower bound, the start, and the upper bound that will be the end. Then with these symbols, we need to do several things. So first, we need to use them in order to map the data into the device. This is what we are doing with the map clause. We are using a start and chunk size in order to map the array X on the device before executing. And then we need to use these symbols as well in the loop boundaries. So we need to start from start, right? And we need to go till end in order to execute the corresponding chunk for that specific portion of the code, right? Then what we have in the right-hand side, what we have is the extensions that we are proposing based on the spread construct. So this is adding an extra level of parallelism. With a spread, what we are doing is, okay, the next loop will be distributed not in a single device, but among multiple devices, okay? The first or the main difference is instead of device, we are using devices in plural, and we are providing a list or a sequence of device IDs instead of only providing one ID. One important thing of that version of the code is that we are not modifying the original code. So this is the loop that we wanted to parallelize going from 0 to n. So we don't need to compute the lower bound or upper bound. It will be computed by the compiler and runtime support. And then the only thing that we are missing from this side is how we are mapping the data. And we are mapping the data with these extra symbols that we are providing, that we are including in the proposal, which is what is the starting point, what is the lower bound of the range that will be computed in a specific device, and what is the size that we are going to compute. Okay, the size will be in number of iterations that will be assigned to a specific device. Okay. So the intent of this proposal initially is not to increase the performance, but to improve or to increase the expressiveness of the model. So what we wanted to do is to improve the programmability of the code, or increase the productivity of the programmer, the program developer, right? That is initially. In the long term, we also wanted to improve the performance, and this is because this new syntax in which we are expressing that we wanted to divide the loop iteration space among multiple devices, we still have room for improvement in terms of load balance. For instance, in the right-hand side version, we are pre-assigning the chunk to a specific device, and we cannot change that. In that version of the code, we can start assigning chunks of code to different devices, and as far as they are finalizing, we can provide more chunks to execute. So we can balance the execution, and balancing the execution, we can increase the performance. Then, what would be the different stages that we are pursuing in that acceleration use case? Okay, the first one, it's already explained. So we are adding that support to the compiler. So the source code is compiled, and we are generating what we call a fight binary. Fight binary in terms that we are not including a single architecture, but we are including two architectures, part that will be executed in the host, part that will be executed in the device. And this is what I was explaining in the previous slides. Then once we succeed with that, we move to the second stage. What we wanted to do is to wrap that binary inside a container. In that case, it will be a Docker-like containerization support. In the project, we are considering Podman. And once we have the binary wrapped in the container, so maybe one thing important that I need to mention here is that the container will need to mount the services in order to communicate with the PCI. So that will be the most difficult part from that specific use case. But in any case, this is something doable, and we are trying to do right now. And then the very last stage will be to orchestrate all the different containers that we have using Kubernetes. I mentioned before that the implementation that we are using is K3s. Okay, so we will deploy all the containers through the platform that we are developing at the RISER project. Okay. Then let me finalize this presentation with a set of benchmarks that we are considering at the moment. This is the list of codes that we are porting to the new syntax. Let me group them in three different areas. So we wanted to focus on linear algebra or dense computational services, because we still wanted to target HPC system. We are including as well certain benchmarks that are more devoted to AI or machine learning. So here we are including the deep neural network algorithm, and also we have the convolutional layers. And finally, we wanted to include some more specific services that could fit more with the cloud environment in terms of security, for instance, and here we are including cryptography, and also in terms of, for instance, image compression in order to handle the images stored in the cloud service. And finally, well, once we solve, we are keeping the set of benchmark very simple at that stage of the project, mainly because with that set of benchmark, we have all the different scenarios that we wanted to solve. In some cases, we have some load imbalance. This is one of the things that we wanted to explore in the implementation, but also because some of these benchmark also includes stencil operations that are imposing certain complexities in terms of communicating device to the device. Okay, so there are portion of the buffer that are computed in one device that needs to be moved to the other device. So, and this is the kind of problems that we wanted to solve before going to bigger applications. And now, just to conclude the presentation, first, what is the current status of the RISER project in terms of this use case? So we have an implementation on LLVM Clang. So we are now able to compile the programs that we have shown in the previous slide, and we are able to execute them with a static scheduler. Okay, so just defining at the very beginning what will be the portion of code that will be executed in each of the devices, and we are able to execute that. We are comparing the performance that we are obtaining, and in most of the cases, the performance is equivalent to the manual distributed version, so that is good. In certain cases, we are detecting some problems in terms of performance because we are serializing the execution of certain kernels. Then we are trying to solve that. Actually, we have already solved that. So we can execute now concurrently. And then there were some other issues related with the block dimensions that we were providing to the compiler that was not honored. And when executing in the device, the thread hierarchy was not properly established. Okay, so we are also debugging that, and we are trying to solve these minor problems before proceeding with bigger examples. Okay. The second thing I wanted to comment in that slide is how we are expecting to impact OpenMP. So the idea is that we are not going to have the proposal as it is right now in the standard, but we wanted to contribute in that discussion. So BSc is part of the OpenMP committee, so we wanted to raise discussion. So the first goal will be now to gather all the data and all the executions and create a publication, and with that publication we'll go to the OpenMP folks and we'll present the work, and we'll start the discussion on how to deal with multiple devices in the standard. And then the very last thing I wanted to comment is that RISER will have a continuation that will be higher. It will be a continuation in terms of the architectures that we wanted to exploit. There will be different goals, and this is something that we are currently defining, and it's already defined in the proposal. But in terms of the acceleration use case, we are planning to continue the work that we are doing in RISER in that higher project. And with that final statement, I finish the presentation. I think that I can stop sharing.
Thank you. Thank you, Xavier.
Thanks to you.
So let me share. So now it's question time. Yeah. So you can submit your questions in the question panel that's in the top menu. We've already had one question. We've been exchanging behind the scenes about this question. So let me find it. Yeah. So we had a question from Jason Adler. Thank you, Jason. Thanks, Utz and Craig. Craig, will RIA 1 support CXL? So we've been exchanging messages in the chats, but the attendees can't see it. So Utz or Craig, do you want to comment on this, or?
Give a quick
So there's two questions,
Craig?
right? I answered one that I think
Yeah,
we posted
so
to everyone. So Craig is
is
on the hook for that.
yeah. Okay. So do you want me to read out your
Oh
okay,
no, I
so
I can repeat. No, that's not a problem.
okay,
So is
yeah,
everybody?
please repeat it for the audience. It
So
will be
the
nicer for them.
original question was whether OpenCUBE.
Will RIA 1 support CXL?
Right.
That wasn't the original question, but we can answer that one. Yes, so we have PCIe Gen 5 interfaces that also support CXL 2.0.
Oh yeah, sorry. The first question was, are you considering CXL support for OpenCUBE? So this first one is for you, Utz.
Right. And so my answer to that is, of course, if we can get it with RIA, it's interesting because, as you saw, we care about different memory tiers very much, and RIA will allow us to do HBM and directly attached DRAM. And so adding another tier and seeing how that could be behind OpenFAM, how that could be used as a resource in Kubernetes, all is fully in scope. there's a bit of a question of timing, right? And also available interesting CXL attached memory. But the question came from Jason, who's with Micron, so maybe
Yeah.
he wants to donate a DIMM or two to us, or give us a good price. Yes, in scope.
Okay, thank you. And so, Craig, what do you have to add on CXL and RIA?
My comment was that where we see a lot of traction with CXL attached storage is for memory sharing in data center, particularly hyperscalers have been driving this. I haven't seen as much traction yet in HPC, but one of the goals with OpenCUBE is to look at how we can intersect sort of classical HPC with more data-centric data center workloads, Kubernetes, integrating things like this, right? So it would be an interesting experiment, I think, for the project. But he did comment on that, and I think he agrees.
Right. And while Craig is right with a difference in customer requests for this, I think even in the HPC space, at least some customers are considering, if not node local extra memory, like the old fat nodes, but they're always too few or too many, depending on how you look at it. So this extra node signable, as I would call it, fabric attached resource is really interesting. If you can kind of judge your workload, how many will need it at any given time. And that's, again, difficult decision to make. But as systems become bigger, you can't just say we need node local memory storage to be bigger and give every node a bit of it, right? So maybe it's really useful to have that heterogeneity we've been discussing for years, even in the high-end HPC market.
Thank you, Utz. I don't see any other question. Oh yeah, there is one. Okay, no, it was an answer from Jason. Thanks, Utz and Craig. We'll follow up with you both on this topic. Okay, so any other question? Maybe while we wait for more question, maybe Manolis, you were the only one who did not talk here. So did you want to add anything about in general, or?
I can fill up some time until we get a couple of people to contribute questions.
I'm
So
doing
I'm
the
the
filling up, but
coordinator.
but I
Yeah,
mean, you're
I'm the
here.
coordinator
We
of
have not heard
RISER.
you, so
Yeah.
yeah.
And my comment would be that we have been in touch with the colleagues of OpenCUBE, and I see very interesting points in the software stack and particularly the storage aspect. Our own project is more into lower level parts of the software stack, and the storage is not covered by us. So we are under the same call and we have this complementarity. That's a very visible part as far as I can tell. So I appreciated having this summary that Utz provided. Our side is more on okay, we have the Cyper RIA server as part of our proposal, but also a lot of prototyping with RISC-V, and a lot of our work is about integrating IP blocks. So that's a particular concern. And I found it interesting the mention to CXL, advanced versions of CXL. It's something that I would have appreciated if we had it available at the time of setting up the proposal. We are at the same point in time as pretty much OpenCUBE, and there are some contributions. A prominent example is what my colleague Xavi presented earlier around runtime systems, ways to deploy on cloud, and I think these are things that will mature and become, at some point, I think they will become mainstream. They're not mainstream yet because they are not, I would say, usable enough and perhaps not robust enough. Yeah, that's my comment on top of what my colleague Xavi said.
Thank you, thank you, Manolis. I don't see any other questions. You confirm, Gabriela? No questions? Okay. So, well, in that case, I would like to thank all of our speakers, many of them today. Craig, Utz, Xavier, anything you wanted to add before we close? No?
No, I don't think so. Again,
Okay.
reach out to us if you're interested, if you want to hear more. There's 2 more projects that are in the same call, vitamin V, and someone helped me with the one with A.
Aero.
Aero, right?
Mm-hmm.
And we're all working for the same purpose, and as Manolis nicely put it, at different levels or different views of the same problem. And we're sister projects, so we're all friendly. If you talk to one, the other one might answer. That's
Okay.
the risk.
Thank you very much, Utz. So thank you, Utz. Thank you, Craig. Thank you, Manolis. Thank you, Xavier, for being here today. Our next webinar will be in May. We'll get back to the SRA6. We still have a lot of topics. Actually, most of the people here, I mean, the speakers here are also contributors to the SRA6. So you know what I'm talking about. So I will open registrations very soon for our next webinar, which will be about algorithms and quantum for HPC. So quantum, it's always a good recipe for success, at least for a webinar. So thank you, everyone. Thank you to our attendees, and I hope we'll talk to you in May about our SRA6. Yeah, I'm still last minute check. No more questions. Okay.
No.
Thank you, everyone.
Thank you. Bye.
Bye bye.
Thank you very much. Bye bye.
Bye. Thank you very much.